Hello, my name is Emilio Artacho, and I will be telling you about basis sets for SIESTA, starting with general considerations of non-orthogonal representations and LCAO. Here you can put a face to the name and to the voice, although what I'm going to be introducing here are related to the work done by many others. Let us start by seeing why we do need a basis at all. So we start with the Kohn-Sham problems, in which we have to solve a Schrödinger-like equation like the one you're seeing right now. So if we do expand the states that we are looking for in terms of a known set of basis functions, the phi's down there in the ket representation, that would be the E sub mu, we can then transform the initial Kohn-Sham problem into this kind of other problem, this generalized eigenvalue problem, which is a very canonical problem in linear algebra. And there are lots of different tools to solve these things, in which we involve two matrices that are the ones defined at the bottom, which is the Hamiltonian matrix, which is obtained from the basis set, which is known, and the Hamiltonian, which is also known, and the overlap matrix, which is also something that we can pre-calculate. Once we do have these two matrices, we can obtain the coefficients that are the unknown. So a key thing is that the unknown is transformed then from the unknown Kohn-Sham wave functions, single particle wave functions, to the unknown coefficients. And if the basis set is a finite basis set, then this is going to be always an approximation. How many do we need to get a good approximation to the original problem? That depends on the quality of the basis functions we chose in the first place. Before we get into basis sets themselves, let us express the particle density, which is a key quantity in density functional theory, when we're actually working with a linear combination of orbitals, of basis functions, as we're doing now. And you can see that the particle density expressed as the sum of the squares of the occupied Kohn-Sham eigenstates. By introducing the expansion I was introducing before, you can get the expression of density in terms of something which is the equation you have in blue, which is called the density matrix. So at the end, we end up with three matrices that are the key matrices for the calculations we're going to be performing within any of these electronic structure codes, which is the Hamiltonian matrix at the bottom, the overlap matrix, and the density matrix. Notice that this overlap matrix that we're carrying is because in general, I'm presuming that the basis set does not need to be orthonormal. And so we have generalized a bit the Dirac's formalism into a situation in which we have non-orthogonal basis sets, which we're going to use definitely for the SIESTA calculations. Let me briefly flag the possibility of describing non-orthogonal basis sets and our dealings with it using a tensor formalism, which is much more adequate to dealing with vector spaces with oblique axes. That is what we are doing with non-orthogonal basis sets. And for that, what we do is we introduce what is called the dual basis. We indicate with the same symbols as before, but with the index upwards. And they are vectors that are defined for each one of the basis states, and that they fulfill the conditions that you can see there upstairs and above. Using these relations, the direct basis and the dual basis, one can go from the Schrödinger equation to something that looks very similar to it. It's quite a transparent formalism, especially for manipulation, for formal manipulation. All of the objects, instead of matrices as such, they are tensors, and they have their up indices that are contravariant indices, the down indices that are covariant indices. And for whoever in the audience that knows how to deal with these things, you'll find that very, very natural. And the overlap matrix that we had before actually is just one of the metric tensors associated to this space, and the other one is the tensor with the two indices up, the S tensor with the two indices up, which is in matrices would correspond to the inverse of the overlap matrix. Let me also state briefly how all this generalizes to the situation in which, instead of solving the time-independent Kohn-Sham problem, I'm solving the time-dependent one, which is what happens when you're dealing with time-dependent DFT. There will be a talk about this in the course in real time. And so then what we're faced is a Kohn-Sham equation that looks like a time-dependent Schrödinger equation. If we do the same kind of expansion in a known basis set that we were doing before, then again, we expressed our equation in terms of the unknown coefficients, and the equation looks like you can see there framed in blue. And it is a very similar construction, except for the fact that now, in addition to the Hamiltonian in overlap matrices, we have an additional matrix, which is the D matrix that appears there, that relates to the fact that the basis sets might be changing in time as well. Of course, if the basis set is not moving, although the electrons might be evolving, then this D matrix is 0. But otherwise, we will have this D matrix that we have to carry in our calculations. So what is actually the meaning of that D matrix? It's a relatively obscure thing, because it seems to be spoiling things like hermeticity and so on and so forth. Actually, it's from the geometrical point of view that we were talking about before. If now we let our basis sets evolve, especially if the basis set is a finite one, then we are no longer in a Hilbert space. Of course, we are in the large Hilbert space, infinite dimensional Hilbert space. That would be the ambient Hilbert space. But the one we're describing with an evolving basis would be a curved manifold within it. Particularly, it would be called the fiber bundle. And so using the kinds of tools with tensors again and so on and so forth, we can define in such a curved manifold a covariant derivative. That is the one we're defining in the corner below. And then the time-dependent Schrödinger equation appears again very naturally in this language. And so that you can look a little bit deeper into if you're interested in it. The most popular basis sets in electronic structure are plane waves and atomic orbitals, of course, of various kinds. And there are many other basis sets being used, but we're going to concentrate on atomic orbitals. The atomic orbitals themselves are defined as wave functions in real space that are the product of a radial shape, depending on the distance to a center, typically put on a nucleus, but not necessarily. And then there is an angular dependence that is expressed with spherical harmonics as eigenstates of angular momentum. Here you can see there are several advantages and disadvantages named. The most important advantage probably is the fact that they are very efficient. You need very few, comparably few functions to get relatively accurate results, or quite accurate results indeed. And that comes with reductions in the CPU time and memory needed for the calculations. There are other advantages listed there, but main disadvantages is the lack of systematics for convergence. It is not obvious how to make your basis set increase or grow in order to improve the quality of your results in an efficient way. So it has to be tried in different ways. There's quite a lot of experience accumulated and so on, but it is not as systematic as other basis sets. We have seen that the angular shape of these orbitals is determined by the spherical harmonics, but what about the radial shape? There is quite a lot of freedom there. And in the history of quantum chemistry from atomic physics, there was the usage has evolved from using atomic orbitals initially, the actual solutions of atomic problems, through Slater type orbitals, Gaussian orbitals, contracted Gaussians, as you can see in the expression, in the bottom expression, all the way to the kinds of things that we're using now, which are radial functions just expressed in a grid as a table of numbers. And they can be constructed from many origins, and in particular, we're going to be using density functional theory solutions of pseudo-atoms themselves. Constrained also to be of finite support, meaning that they are going to be strictly zero beyond a cutoff radius, which is going to lead to sparse matrices and it is one of the ingredients behind the linear scaling capabilities of SIESTA. So in order to construct the basis, we normally start with what is called the minimal basis, which is the set of occupied or partly occupied L shells of free atom. So here you have some examples of a single zeta or minimal basis for oxygen or iron. And then once you have that, you increase radial flexibility by doubling the basis, double zeta. That would be 2 orbitals of different radial shapes for each one of the previously defined, and they would act as independent basis functions. And then you can go to triple zeta, quadruple zeta, and so on and so forth. In addition, you can increase angular flexibility by introducing polarization orbitals. That means orbital shells of orbitals with an angular momentum which is larger by 1 of the largest angular momentum that you had in the valence before. In addition, you can also introduce diffuse functions that would be wave functions that are decay slower than the ones you find in the free atom. So normally these kinds of bases are grouped in tiers. So one starts with a minimal or single zeta, and then if you want to increase every step of the improvement, in every step you increase by 1 zeta level and by 1 polarization level simultaneously. So you go from single zeta at tier 0 to double zeta p, double zeta polarized, tier 1, triple zeta doubly polarized prime in tier 2, and so on and so forth. Let me make a very important point concerning the accuracy of LCAO. Remember that in quantum chemistry, a gold standard of accuracy is given by coupled cluster theory with singles, doubles, and triples, and so on and so forth. All of these calculations are done with LCAO. So golden standards of accuracy are using atomic orbitals as basis sets. So the accuracy of the basis is controlled by you, the user. There is a usual trade-off between accuracy and efficiency, of course, and the more accuracy you want, the more you have to pay. But it is an important thing to bear in mind. And actually the needs depend very much on the system you're dealing with, the property you're after, and the problem you want to solve. And so then you are responsible of the choice of the appropriate exchange correlation density functional, pseudo potentials, and basis set, in addition to the technical parameters you need to converge. Please be aware of all the statements that you see in communities about SIESTA is more efficient than that, or less efficient than that, is more accurate or less accurate than that. Actually, these statements typically depend on the approximations, not the method. In principle, SIESTA allows from very, very efficient to quite accurate to very accurate calculations, and it depends on what you do with it. So in that sense, the SIESTA basis sets themselves are the only requirement associated to them is that they are atomic-like, as stated before. You can center them wherever you want, but the only other requirement is that they are of finite support. That means that the wave functions themselves have to be strictly zero beyond some distance from the center you've chosen. And in principle, there can be as many as you want in zetas and L channels in polarization of any radial shape you want and of any cutoff radius you want. And they could be centered anywhere, as I was telling about before. So even in principle, you could use a radial shape as the one shown here. So with that, I conclude this very first talk on basis sets, in which I've told you a little bit about how to transform a Kohn-Sham problem into a linear algebra problem, the formulas for non-orthogonal basis, and different kinds of basis sets, but centering on LCAO and SIESTA. In the following talk, we will be seeing how to construct basis sets, in particular for SIESTA. So there are some tools that SIESTA provides in order to generate basis sets with different degrees of automatism. We'll see about that later.